welcome to Math Stack. Sorry, just Math. I don't even have to fix it. Welcome to Math 331 problem solving. We'll say lecture 23 or 24, maybe 24. We are doing the geometric proofs today. The goal is to give at least one classmate an A+.
Great. So if you guys remember...
so the significant contribution to the class.
Okay, you guys can talk first.
Okay.
Yeah,
the inequality of points becomes even worse. So for those of you who don't contribute, if other people do it,
oh dear.
your grade could actually fall below a 0.
Wow. Like you.
Okay, so I'll just review the square root of 2 case real quick first. So our setup there was like this. So here. Right, and then we had this big square have side length A, and then the smaller square have side length B, right? And this square is the same as this square. And we start off by saying A squared equals 2B squared, right? And that also gets us the equivalence A over B is the root of 2. And we assume that A and B are integers and minimal, right? So what we did in the 2D case basically is that we said, well, this plus this has to equal this, right? And that got us a method of descent, but basically the geometric idea is that, well, I said that the smallest case where 2 squares add up to a bigger square was this bigger case, but then I found another case where these 2 squares add up to this square, right? So that's a contradiction. So for this 3D case, let's just make this.
Is everybody comfortable with the two-dimensional case? And the point I just want to emphasize, just to make sure that we're clear on what is a geometric proof. We started off with 2b squared equals a squared. So 2 of the smaller squares equal the larger square. And then over here, we get this new doubly counted square. And then we have these 2 ones that are not counted at all. And now we have these 2 add up to this. So you still have another geometric picture.
Okay, so kill that. So for the cube root of 2 case, we'll have this. Now just imagine this is a... Congratulations.
Let's be paying attention.
Imagine that this is now a top-down view, right? So this, instead of being a square, is now a cube, and it just extends. So you're looking at it top-down. And then you have the same idea with a cube of side length B inside it, cube of side length B. Imagine that this cube starts at the bottom right-hand corner, right? So if you have a cube like this, it starts here. Then this one starts here on the top left. So basically, exactly what you see, but this one is just up and this one is down. So then they come up and meet in the middle here, and that gets you another cube, right? So the side lengths are going to be, here is going to be A minus B, right? That's the same as the 2D case. And then we also need this stuff. So, sorry, we still have the same idea. The empty space that isn't covered by any of the inner cubes, the smaller cubes, is still equal to this overlapping volume. Right, but the empty volume is now not just the corners, but you also have the little bit of space here and here, where the cube doesn't come all the way up because it's height B instead of height A now. So I just split it kind of like that.
Is everybody understand geometrically opposite diagonals?
Makes sense, okay. And then this here, because this comes out B, is also side length A minus B, right? So then this is just going to be A minus 2 of these, which is A minus 2, A minus B, right? And that gets you to 2B minus A. So that's the breakdown there. And then everything here is just the same stuff. Okay, so now we just calculate the empty space volumes. So this is going to be A minus B, and then since there's no like smaller cubes anywhere in this region, it just has a complete height of A, right? So that's going to be A minus B squared times A. And I'll just do here, here, and here, because you have exactly the same thing, so I'll just multiply this stuff by 2. So here, this space is going to be 2b minus a, and then from here to here is a minus b, right? And then since b of it is covered by the cube, you have a minus b of it, that's empty space, right? So now it's going to be, what is this showing? I think it's showing. Sorry, so 2b minus a minus b, and then the height is a minus b. So a minus b squared, 2b minus a. And then lastly, this space has the same height, a minus b, because it's on the same space of just being that difference between the smaller cube. So a minus b, b, and a minus b again. So a minus b squared times b. Okay. And then this part right here is just going to be this, right? But it's going to have the same sides everywhere. So it's just going to be this cubed, because you can see it. It's the same idea. You have a minus b here, so you get that math, and then the height is the same. So the volume, I guess this is volume 2. Volume overlapping is 2b minus a cubed. Okay. And then the empty space is all of this times 2. But if you realize you can just factor out an a minus b squared. So you get a minus b squared times a plus 2b minus a plus b. A and a cancel. 2b plus b is 3b. Right? So now you end up with 2 times 2b minus a. Sorry, a minus b. A minus b squared. 3b equals the overlapping volume, which is 2b minus a cubed. Good so far? Okay, so this is where it gets slightly non-geometric. That's where the controversy comes in. So divide both sides by this, right? I get you to get 2 equals 2b minus a.
Wait, what was this?
Oh, sorry. This stuff.
So
just leaving 2 on the left side. Huh?
Where's the 3b?
I'm also going to divide by 3b. 2b minus a cubed.
I'm sorry, is everybody okay with this where he counted everything once and then doubled because each piece occurs twice? That's where the 2 comes from. And they all had an a minus b squared in common.
Okay, so just rewritten over here. But remember, initial definition of 2, right? Back to here, a cubed over b cubed equals 2, right? So I plug that in over here for 2. You get a cubed over b cubed is 2b minus a cubed, a minus b squared, 3b. Look okay? All right. So now the key is that, so this is an integer, right? A minus b is an integer. Square it, so an integer, 3b integer. So this whole thing is an integer. So I'll just write this as, I don't know, denominator, denom. I don't want to rewrite it. Multiply. So basically, multiply both sides by it. And then,
Just write it.
okay, sure. Fine. So a minus b squared 3b equals, now a cubed down here, b cubed up here, 2b minus a cubed times b cubed over a cubed. Right? Okay, so this is an integer, which means this right-hand side is an integer, right? But if this is an integer, that means a cubed has to divide b cubed or 2b minus a cubed, right? But since we assume that a and b are minimal, that means they're relatively prime, right? So a cubed can't divide b cubed. So then a cubed has to divide 2b minus a cubed. But then from that, you know that a has to divide 2b minus a. But then since a divides a, right, a has to divide 2b. And since a doesn't divide b, a has to divide 2. Right? So basically, you're essentially almost already done. But you can also say, okay, well, that leads us to a equals 1 or 2. If a is 1, then, well, it doesn't work. And then if A is 2, then B has to be 1, and you have 2 cubed equals, or yeah, you have 2. Oh, right, and then you have, wait.
Well, if A is 2 and B is 1,
Oh, yeah,
then
sorry,
you
sorry,
get
sorry.
the cube root of
Yeah.
2 is 2.
Yeah. Yeah. So the issue with that is that it's not solely geometry, perhaps, because it starts with a geometric idea, but then what you have to use is that in this case, because I'm saying that this is an integer, I need the fact that a cube has to divide either this or this, and that isn't necessarily a geometric idea.
Right, see, over here, the contradiction we get. So the contradiction we get over here is that we assumed we had the smallest square where this worked. And then we generated a new square with the smallest side, and that was a contradiction. Here, something was implicitly assumed. And if you don't think it was implicitly assumed, I will give it to you right now as a test question. Ah, yeah, I saw people looking a little more work. What was implicitly assumed in the algebra that he did?
A, B, lowest terms?
No, you could always assume A and B are in lowest terms. You could always assume that you've removed all the common factors initially. That's fine. Or you can assume that A and B are the smallest numbers that work. That's fine. But there was something he assumed as he did the algebra here. It's true. It's an important result, but it needs to be proved.
Non-zero.
Nope. So we have, this is an integer, this is an integer, this is an integer. So a cubed has to go into 2b minus a cubed, b cubed. And then he said, we know a and b have no common factors, so a cubed goes into 2, yes?
A cubed needs to go into that thing cubed, so you go into 8.
You're on the right track. So we know, so let's assume we just pull out the 3's. And let's just look at this thing over here and say, look, if we don't start off with an integer, we have a rational number. No cube of a rational is an integer except for an integer. Right? If you've got a denominator when you cube things, I'll allow you to assume that for now if you want. But we've got, this must be an integer. And we know therefore that a cubed must divide the numerator. And then he concludes, because a does not divide b, a divides 2b minus a. How do you know that a divides 2b minus a? So if I give you 6 times 25 over 10, does 10 divide the numerator?
Yes.
Does 10 divide 6?
No.
Does 10 divide 25?
No.
So how can he conclude that a divides? I'm sorry?
I said, oh, I see what you're saying.
You assume that A and B are relatively far.
A
Okay.
and B have no common factors.
So
Okay.
So we can't run into this.
If a divides bc, then a divides b, or a divides c.
So like all the common factors have to be in the other term. So
And a and b are relatively prime. So if a and b are relatively prime, then if a divides a product,
all the factors are in the other.
right. So does everybody understand what's being assumed? That if a is relatively prime to b, and it divides the product, it has to divide C. You should not be playing with the two.
I'm sorry, I'm confused really quickly. I think that I wasn't sure, like, maybe the two-dimensional one, or sorry. These numbers are not relatively prime, correct? Or
No, the numbers he's using are relatively prime. But what I'm saying is he's using the following fact, that if a number divides a product, if A is prime, so let's assume A prime, then A divides B or A divides C. And then what you could do is you could write A as a product of prime factors, and since none of A divides B, you would then get every factor divides C. This needs to be proved. This is one of the things that is subtly assumed by many college students. So one of the possibilities for today is we can actually talk about how would you prove this. This is what stopped the Greeks from proving that the square root of n is irrational if n is not a perfect square, is they had to do things by brute force. When you do the square root of 2, you got 2b squared is a squared, so 2 divides a squared, so 2 divides a, so a is even. So a is twice alpha. Then you get 2 divides b squared, so 2 divides b, so b is equal to twice beta. And now you've shown 2 divides a, 2 divides b, a and b aren't minimal, or a and b aren't relatively prime, and you found something smaller. So this is why I'm arguing this is not a geometric proof, because the final step is actually a key number theory algebra statement. Also, of course, you could just write, well, 2b cubed equals a cubed, and since a and b are relatively prime, you're done. And you get to here faster. What you want to do is you want to use the fact that this over here, that's a cube. Actually, that's 2 cubes, or it's the cube 2b minus a times b cubed. So you need to somehow write a cube as a sum of 2 small cubes. So one possibility is to try to say, well, rather than just doing 2 cubes in the opposite diagonals, what if you used more cubes? What if you used 3, 4, 5, 6, or 7? Why not 8?
8 is a perfect cube.
If we try to use 8,
You're trying to prove that 2 is irrational.
bless you. Oh, but maybe it's nicer geometrically to work, and maybe we have something double counted. If we go back to the original square, what if we tried to put things in 4 corners? Is there a way to make an argument like that work and get something? So now, if we did that, we'd have 1, 2, 3, 4. So now this would be counted 4 times. This would be counted twice, 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 once, 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 once. Could you somehow turn that into a proof that something is irrational? I'm not sure what. Maybe you still start with this is A and this is B, and you look at what happens when you put 4 of those in. And maybe that just has nicer geometry. I'm a little bit worried because 4 is a perfect square. The other ideas for... So maybe something like that would work well. The other possibility is to take a equilateral triangle, and the one-dimensional case was to do something like this, and now build maybe tetrahedrons coming up, and see, could you get maybe the cube root of 4 coming from something like this?
I will say you run into a lot of dead ends once you get into the 3-dimensional case with cube roots.
So, again, we have a start towards the A+ here. If anybody wants to help, this will lead to a publication. This will lead to an A+ in the class if it is solved, but it's got to be solved geometrically. So I am friends with the son of the mathematician who came up with the geometric proof here. And so I will have them be the arbiter of whether or not it is an acceptable geometric proof. Over here, right now I would say the crux of the argument, the final key step, is not a reduction to a smaller case. In the proof here, it's a reduction to smaller squares. Whereas here, it's a reduction to essentially if a prime divides a product. So anyways, so thank you for sharing. So we
I'm like 98% sure that like you can't get to the sum of two cubes equals a larger cube with the three-dimensional just two cubes.
right. And this is why I'm wondering, would a tetrahedron maybe work better if you did 8 things with, I don't know. But I'm just worried that you're not going to get a cube plus a cube is a cube. And the contradiction here was we got something smaller.
Right.
We got that same relationship with 2 squares adding up to a square with the smaller sides. And so we've got a couple of minutes left. I want to start by talking about this. If a prime divides a product, it divides at least one of the terms. And the reason I think that this is worth spending some time on is it is so easy to make assumptions when you are doing problems. And that's why this is a really good thing to discuss. Frequently, we do not realize when we are making assumptions. Sometimes the assumptions aren't that bad. Other times, they are. We did Russell's paradox earlier, where you can't form the set of all elements that aren't elements of themselves. Did we do Russell's paradox?
Actually, I'm in pride real, so maybe I
All right. So let R be the set of all x such that x is not an element of x. So this is. So this is one of the greatest shit moments in mathematics. So the great theoretician Frege was building up set theory. He had this massive work putting set theory on rigorous foundations. And the story is the graduate student Russell says, well, what about the following? Which just destroyed the theory and showed that set theory was not being built on solid foundations. So we're going to form the collection of all things that are not elements of themselves. So if you look at the set of teams that have won the World Series, the set of teams that have won the World Series is not itself a team that has won the World Series. If you look at the set of real numbers, the set of real numbers is not itself a real number. Most things are not elements of themselves. What's the most natural question to ask?
Is R and R?
There's 2 possibilities. Yes? No. If yes, R and R, well, R is the collection of all things that are not elements of themselves, so therefore you immediately deduce that R is not an R. Contradiction. Therefore, R must not be an R. Well, we got a few minutes. Let's see what would happen if we write down R is not an R. What does that immediately imply? R is an R, because R is the collection of all things that are not elements of themselves. Therefore, you deduce that R is not an R. Thank you. You then immediately deduce that R is an R, a contradiction. So R is an R precisely if it's not in itself. So what this tells you is R is not a set. You cannot just collect all objects that have a given property and say that is a set. You have to build things up very carefully. What is the only set we really know exists? The empty set. So how many of you have not seen real analysis, where they build up the reals carefully? At least once in your life you should see the reals and the integers built up carefully. So we start off with the empty set. Can anybody give me a new set? What is 1? The set What do you mean by contains one? I don't know one.
Empty set.
The set that contains the empty set. Can somebody give me a new set?
Set that contains the last thing.
So one possibility is you could do this. The set that has only one element, the set that contains the empty set. But there's something else we could do. Yeah. And then the next one is the empty set, the set containing the empty set, and the set containing the empty set, and the set containing the empty set. What number should I associate with the empty set?
0.
What number should I associate with the set containing the empty set? Next one. Next one. How many elements does n have? If I continued, how many elements would 4 have?
4.
How many elements would 5 have? So each set, the set that corresponds to n has n elements. You understand what it means for 3 to be less than 4? I do not need to explain this. Yes, this is acceptable. Does everyone agree that 2 is less than 3? Notice that 2 is actually contained in 3. Notice that 1 is contained in 2, which is contained in 3, and 0 is contained in 1, is contained in 2, is contained in 3. So less than is basically set inclusion. This is one way to build up the integers. You would never want to work with the integers like this. So this is Russell's paradox, and this consequence, which you do a little bit in real analysis, is that you have to be careful in building up sets. So there was an implicit argument made when we were doing the cube root. If P divides AB, that implies P divides A or P divides B. And we'll say P is prime. This needs to be proved. So there's a lot of ways to do this. Has anybody seen a proof of this? Okay, do you remember how you would prove it?
Can we have the fundamental theorem of algebra?
So, not algebra. No, not algebra.
Or is it, it's
Fundamental theorem of
it's the one where you can put any number as a prime of the prime.
and you can do it uniquely if you write the primes in increasing order.
Yeah.
The fundamental theorem of arithmetic. The fundamental theorem of algebra is a polynomial of degree n has exactly n roots. So if you know the fundamental theorem of arithmetic, then you write A with its prime decomposition, B with its prime decomposition, and then since you have a prime on the left, you have a unique decomposition. This means there exists an n such that np equals ab. And now since p occurs in the prime factorization on the left, p has to occur in the prime factorization on the right. We have a unique decomposition of numbers as products of primes. So this is one way to prove the result, but unfortunately to do this now, you need to have proven the fundamental theorem of arithmetic. So it's good to get a sense of how deep is a result. What do we need to make things work? So any other thoughts on how you might try to prove something like this? So let's see, how many of you have taken abstract algebra? I have to make sure I keep my hand down because I have never taken the class. Yeah, I actually got through the math major without taking abstract algebra. I took Galois theory, and I've taught abstract algebra, but never taken it. So let's assume the GCD of P and A equals 1. I'm sorry? Okay, so let's assume A and P are relatively prime. So the question is, how much do you know about the GCD and what do you need to prove these facts? So one thing is, there exists alpha and beta such that alpha p plus beta a equals the GCD of PA equals 1. For those of you who've taken abstract algebra, does that seem familiar? The question is, what do you need to prove that? Now, once you have this, what should I multiply both sides by? So what do I multiply both sides by? What am I trying to prove? We've assumed P is prime, P divides AB, P divides A, or P divides B. We're assuming P is relatively prime to A. What are we trying to prove?
P divides B.
P divides B. We have this beautiful expression here. What should I multiply both sides by? B. If I multiply by B, you get alpha PB plus beta AB equals B. Does P divide the left-hand side? Yeah. We know P divides P, and we know P divides this. So P divides alpha PB plus beta AB, therefore P divides B. So if you can prove that there's always an alpha and a beta such that alpha P plus beta A is the GCD, you're done. So what I want you to do is I want you to actually try to prove this. Or prove in some way, if you want to use the fundamental theorem of arithmetic, you're welcome to do so, but you must prove the fundamental theorem of arithmetic. Okay? For the sake of this homework assignment, there has been, unfortunately, a nuclear blast in the atmosphere. The EM pulse has wiped out all electronic devices. The internet is gone. Your computers are gone. Hordes of survivors have burned all the books for warmth. There are no materials for you to use except what's inside your noggin.
And the professors have been taken hostage?
The professors, it's really sad, but we exercised our escape option. There is no one for you to talk to. The TA is alive, though, fortunately. And you are all alive, and you all can talk to each other. But you can't use any books, you can't use any resources. I want you to try to prove that if a prime divides a product, it has to divide at least one factor. I want you to get a sense of how difficult is this, and just see how easy it is to be assuming something. When we were doing the proof, everything seemed fine, but there was that one step where we assumed, well, because A and B are relatively prime, then A cubed divides 2B minus A cubed, so A divides 2B minus A. That's an assumption. It turns out you can prove it, but it's something that needs to be proved. So I want you to try to prove this to get a sense. We sometimes use this to get a ranking of different proofs. Which proof is better? Sometimes it comes down to how deep of a result do you need to use to prove what you want. And here, this is actually a major thing. So Professor Silva and I actually wrote a paper on how to do this. And so I will send you an email to that paper, but unfortunately, as I said, there's been an electromagnetic pulse, and your email will not work until after you think about this. You don't need to hand this in. This is just on the honor system. I just really want you to try to play with this and get a sense of how hard it is to prove some of these statements and how easy it is to be accidentally assuming something. And again, this is one of the lessons of the class, is to be aware when you are making these assumptions.